Good morning to everybody. We are starting with a new lecture, and this lecture, as you will see here, is devoted to and this is only the first part because the lecture 5 is divided into two different parts. The first part is dealing with the interaction between the electromagnetic energy and surfaces, while the second part will be devoted to the same topics, but from another point of view. So let's start with that, just mentioning the facts that the division in two parts is related to the fact that this topic that is related to the point C of the general schema that I did introduce in the first lecture. So now we need to investigate the interaction between the energy that was emitted by the sun, bypass the atmosphere, and is incident on the surfaces that are based on the Earth. And so the fact that we are dividing the lecture in two is devoted to the fact that we need to approach this particular topic that is very important for the remote sensing course into two different aspects. The first aspect, that is the topic of this first part of the lecture 5, is related to the geometrical aspect of the surfaces and how this geometrical aspect could be correlated to the wavelength of the incident energy, while the second part will be related mainly to the fact that we will investigate not the geometrical characteristic of the surface, but the way in which they are reflecting energy, especially from the spectral point of view. So we have two different characterization of these topics, and now we are starting with the first one. So, as mentioned in a previous chapter, the radiant cell is the most important of the physical quantities in remote sensing, because in fact it is the primary measurement quantity of the interaction processes between electromagnetic energy and the surfaces. You remember when we mentioned in the radiometric quantities, the different radiometric quantities, we mentioned that the detectors mounted on board of the sensor of the satellites are mainly recording radiance that is coming from the Earth's surface. So the whole process of interaction with surfaces follows the principle of conservation of energy expressed by the Kirchhoff Relation, whereby, as we all know, the three coefficients, so the rho coefficient, that is the reflectance coefficient, the alpha coefficient, that is the absorption coefficient, and the transmission coefficient tau, the sum of these three coefficients is equal to 1. So this coefficient, of course, represents the fraction of incident energy that is reflected, absorbed, and transmitted. It is evident that for opaque bodies in certain spectral intervals, and this happens for the most part of our sensitive experience, the value of tau, the transmission coefficient, is 0, or in any case negligible. So the components of the balance are reduced to that of reflected energy rho and absorbed alpha. So we mentioned the fact that in many cases, especially when we are acquiring data from satellite, so from using sensors that are very far from the surfaces, almost all the Earth's surfaces are to be considered opaque. So the tau coefficient is equal to 0. So recalling that the energy absorbed serves to thermally charge the body in question, and they trigger the phenomenon of the emission of electromagnetic energy, regulated in turn by the emission coefficient epsilon. You remember we also mentioned this emission coefficient epsilon. The radiant flow coming from a generic surface substantially includes the contribution of two different components, that of the reflected energy and that of the energy emitted. So here is quite important to mention that when a surface when we are recording energy that is coming from a surface, this energy is composed by two different fluxes. One is related to what is reflected, and one is related to what is emitted. All right, now, as I mentioned at the beginning, we need to take into consideration the radiation's geometry. So, geometry of the radiation is the descriptive study of the position relations of the surface, of the source, and the sensor with respect to the observed surfaces, as shown in the following figure here. So, the scheme shows two radiant flows. One incident that is called phi, and the other outgoing that is called phi1. So you see, look at the mouse. This is the incoming, and this is the exiting flux. And affecting a point Q, that is here, this point Q, on an elementary area dA belonging to the generic surface S. Here you see the dA surface that is belonging to this general surface S, from which two symbolic cones branch out with enclosed radiance subtended to the inside of their respective solid corners. So I mean, this is the energy that is coming here, and this is the incident angle theta, and this is the outgoing angle that is theta 1 with respect both to the normal n to the point Q. So you see that the energy that is reflected or emitted from a point Q is propagating in the space for a specific solid angle, and this is assimilated to a sort of cone. You see here, this is the general geometry, the radiation geometry. All right. A reference symbology is used to distinguish the two conditions of incident and outgoing radiation. Let's recap that. By convention, the angles with respect to the normal, so the zenithal position n, and to the direction d azimuth, are indicated by theta and phi if referring to the source incident flux, and with theta 1 and phi 1 respectively when referring to the direction of observation, so the outgoing flow. Similarly, the radiometric quantities observed in the case of possible confusion of terms will be distinguished from those incidents for a first apical, with the exception of those that are distinguished by their own definition, such as irradiance E and excitance M, that are two quantities that we already know very well. All right, so let's continue with the radiation geometry. From the physical point of view, the surfaces involved in the radiative transfer phenomena have a variable behavior, in the sense that they do not always maintain the same characteristics in all the direction of observation. And this is quite important. In fact, we have that in bold. Indeed, natural surfaces generally behave in an anisotropic manner. For example, they direct not uniformly their radiance in different directions depending on their structure and geometry. Sometimes, however, in conditions very close to the ideal ones, they can be assimilated to isotropic surfaces, so that the radiance is distributed uniformly in space. So that means that, usually from the theoretical point of view, and it is important in the first phrase that is in bold, do not always these surfaces maintain the same characteristics in all the direction of observation. That means that, if they are reflecting energy, maybe this energy is not reflected in the same way in all the angles. And on the contrary, there are some surfaces that, as we can read here, can be assimilated to isotropic surfaces. What does it mean, isotropic surfaces? That the radiance, being or reflected or emitted, is distributed uniformly in space. So that means that if you are looking at these surfaces, these isotropic surfaces, from any point of view, the energy that is going straight to your eye is uniform. Is the same from whatever position you are looking at these surfaces. It is useful to remember some reference models among the many possible ones that allow to simulate in a simplified way the real situations, as in the following schemes. In relation to the portion of space considered, directional, conical or hemispherical propagation can be mentioned, depending on whether the radiation affects a simple direction, a solid angle, or half space, respectively. So let's talk. So having these three possible configuration, let's talk about a new subtopic here that is related to specular and Lambertian surface. So, specular surface is defined as a surface whose observed radiance values L that are referred to theta 1 and phi 1, so this is the reflected or emitted energy, is reflected in one specific direction, where R is equal to I. So that means that are specular all the surfaces in which the incident angle is equal to the reflection angle. Lambertian surface is defined as a surface whose observed radiance value, the same as before, is constant for any combination of geometry between the source and the observation point. The surface takes on the meaning of integral diffusor, and like a black body, it's only an ideal model. So, a good approximation of a specular surface can be a mirror, while for a Lambertian surface can be, for example, the screen of a cinema, constructed in such a way as to reflect the light in almost the same way in all directions, so that from any position the spectators can see the projection at best. Natural surfaces, although sometimes approaching this model, generally exhibit more complex behavior. So now we are introducing through very theoretical geometry of when we are talking about reflection. So the specular surfaces and the Lambertian surfaces. So we mentioned the fact that in the specular surfaces, the energy is reflected in one specific direction with an angle of reflection that is the same with respect to the normal of the point to the incident angle, while for Lambertian surfaces, the reflection mode is totally independent from the incident angle of the energy. So whatever is the incident angle, the surface will reflect in all the direction towards the observation points. And you see, two kind of there are in reality these kind of surfaces. For example, think about a mirror for specular surface, or the screen of the cinema, or a screen of, that we are using in class for our video projector. that are a particular screen that are a Lambertian diffuser, a specular diffuser, a Lambertian diffuser that are able to reflect the same quantity of energy in all the direction in order to allow I mean, the spectators, in the case of the screen of cinema, or the students in the class, to see in the same way whatever is the position from where they are looking at the screen. All right, this is an example of what I'm mentioning. So you see that this is the behavior in the left figures of specular reflection, and this is the case of diffuse reflectors. So you see that the specular reflectors are reflecting in one particular direction, where you see these angles are the same, while for Lambertian or diffuse reflectors, you see independently from the incident angle, the surface is reflecting in all the direction. Here we need to take into consideration two extra conditions. The first condition, as you see here, we are talking about a reflection, because here we are particularly involved in reflection. But you see the extra condition, you see that for both the surfaces we have opaque materials. So that means that if they are opaque, there's no transmission. So that means that the transmission coefficient tau is equal to 0. So that means that for the Kirchhoff's law, alpha plus rho is equal to 1. So that means that if the surface is reflecting energy, that means that rho will be more than 1, and for the same is the same for the Lambertian reflector. The second condition, you see, is that you have here the symbol of our eye. That means that we are observing, or there's a sensor that is observing these things. But consider a very important thing that we can introduce in this schema. That usually, I mentioned the facts that in the first lecture, that for remote sensing, usually the sensor that is mounted on board of the satellite is not in that position, but is acquire nadirly the reflectance. That means that is here. Look at the mouse. It's in correspondence to the normal of the surface. So this is very important, because you see that if the satellite, the sensor that is mounted on board the satellite, is acquiring a reflectance that is coming from the Earth's surface, and these Earth surfaces are behaving like specular surfaces, that means that if the sensor is here, it's on the normal of the surface, it will not receive any contribution from the Earth surface, I mean a reflectance coming from the Earth surface, simply because if the surface is a specular, the reflection will be in another position in consideration and regarding the actual position of the sensor, because the sensor is perpendicular to the surface. So if from satellite we are acquiring data over specular surfaces, that could be the risk that the sensor is not recording anything, just because the reflection is divergent from the position of the satellite. Why? If we are acquiring reflectance that is coming from Lambertian or diffuser reflectors, that means that if we are here and the surfaces on the ground are reflecting energy and are reflecting in a Lambertian way, that means that independently from the angle from which the sun is emitting energy, part of this reflected energy will be strike over the detectors of the sensor. So that means that, you see, it's very different from this point of view. And of course, if you are here, if you are perpendicular to the surface and you are registering zero value, that means that the surface that is reflecting in this point is non-reflective, so is characterized by a reflection coefficient equal to 0. That means that, if this surface is assimilated to a Lambertian one, that means that we are sure that this surface is not reflecting. While if we are in this left condition of the figure, so if you are taking into consideration a specular reflectors and we are registering a zero value, we have a couple of different alternatives. The first one is that this point here is not reflecting any energy. The second one is that this point here is reflecting energy, so that means that the reflection coefficient rho is not equal to 0, but is simply reflecting energy divergent from the position of the sensor. So you see that it's very tricky from our application point of view, because if we are facing specular surfaces, we are never sure of which is the process, if the surface is not reflecting or is it reflecting in another direction with respect to the position of our sensor. So let's go on. In the case of a perfect diffuser that is a Lambertian, the observed radiant intensity I depends only on the incident radiant intensity according to the normal and on the cosine of the angle of view theta 1 with respect to the normal n. Essentially, the radiant intensity value at output I decrease in a linear mode with the increasing of theta 1 according to the following relation that is called cosine law or Lambert's law. So, in this case, you see, the energy that is reflected is depending from the cosine of the reflection angle. And in order to verify the trend of the radiant cell with the variation of the observing position being equal for the what we said before, being valid this expression, that means that we can substitute the different quantities here, and you see we can we can arrive to this just simplifying the two cosine that we have in the two different terms of this equation, and we can arrive to mention that from this last relation, in the case of surfaces or means with Lambertian behavior, because we are talking about Lambertian surfaces, the observed radiance L, this one here, no longer depends on the observation geometry, but simply on the intensity of the radiant flux, according to the normal and to the extent of the area involved A. So this is something that we already mentioned in the radiometry part. Well, you see, when we are talking about Lambertian or surfaces, the intensity is depending only on the intensity of the reflection, and depending only on the intensity of the incident radiation and on the area that is involved in this radiation. In the case of a radiant flux coming from an infinite distance, that is, for example, our external source of energy, that is the sun, or in any case from far away with respect to the dimension of the interested area, such as, for example, the sun to the earth, the radiant flux can be represented by a set of parallel rays. So this is very important, and this is the figures. So you see that the incident energy E0, could be thought as parallel fluxes, parallel electromagnetic radiation. So we don't need to take into consideration the facts that the energy is starting from a particular point in an infinite position, but we can consider all the energy represented by a set of parallel eyes, in which you see here all the energy that is insiding over the surface, dA1, can be seen by for example the sensor that is in the position perpendicular to the normal n is equal to dA1 to multiply for the cosine of the theta angle. So this is the quantity that is observed by the sensor that is mounted on board the satellite, that is here perpendicular to that position. Alright, in these cases, the angle of exposure theta of the affected surface is day1, defined by the normal n to the surface, and the direction of the incident flux, d phi, is very important. In fact, for conditions in which theta is different from 0 for simple consideration of the projective type, the surface dA1 will always be greater than the normally exposed dA of an inverse factor to cosine theta with the latter, vice versa reduced by the factor cosine theta. By definition, E0, the irradiance, is expressed by the following relation, because this is what we mentioned in the radiometric system, so is the quantity of flux for unit of area dA, and where the index 0 indicates the angle value theta equals to 0 in the normal condition. So in the normal condition, of course, all the energy depends only on the area that is reflecting this energy. So what we will mention later on as the geometric resolution of our output image. For any other surface, dA, oriented differently from dA, the relation is then that this energy that is reflected will be inversely proportional to the cosine of the incident angle, and considering that the irradiance E theta for a generic oriented surface is given by this quantity, you see, as mentioned in the radiometric system, so that means that by replacing we will have that the results will be that E theta will be the irradiance in the 0 position multiple times the cosine of theta. And in this case, we can calculate the irradiance phi when E0 of the exposure and the angle phi are known. So I mean we can understand phi of theta. We can understand if the position of the sensor at the angle of incident is known, and this is known usually in remote sensing, we can calculate this irradiance, that is the energy that is reflected by a particular point on the Earth's surface. Concerning the conical radiant flux condition coming from a point source, given a point-like electromagnetic energy source Q, for example the Sun, which radiates in space with intensity I, to define the irradiance value E that affects a generic surface D1 located at a distance R from the source, and this is the example, you see, we have this point, point-like electromagnetic energy source Q, that is irradiating to a particular distance R from the source in a given surface with a particular, you see, dA1, a particular attitude in correspondence to the to the point in which this surface is seen, for example, by a sensor, and this is represented by this angle, we can calculate the quantities in these terms, because by definition the radiant flux intensity is again this one, so in which I is the ratio between the phi and the omega, and the omega is the solid angle subtended in Q by the surface dA perpendicular to the direction of the flux. Expressing the value of the solid angle d omega according to the area dA1, we can get that d omega is the ratio between the A and the R with the power of 2, and considering that the A is also be calculated by dA1 times cosine theta, this is the equation that is that linked d omega with the seen surface. Alright, this is very important to calculate this quantity, that is the energy that is reflected by a particular surface if seen by another point of view. What is happening in reality when we are looking at a particular surface from a point that is not really perpendicular, or what is happening from a generic point of view when we are acquiring data from satellites, in which usually the sensor is mounted on a platform that is perpendicular to the point, but in which the energy that is insiding from the sun could be have a different angle, just because the attitude, I mean the height of the sun is different. It is depending on the hour of the day in which we are performing the acquisition. So replacing the initial intensity relationship, so we can just represent the irradiance in this way, where theta is the angle between the normal n to the surface dA1 and the direction of the radiant flux d phi. Finally, by expressing the last report in terms of irradiance E, we can get this relation here, where the irradiance E is simply the ratio between the I cosine times cosine theta divided by the second power of R. Alright, it results that the irradiance E coming from a point source towards a generic surface D1 is proportional to the value of the radiant intensity I to the source and to the cosine of the angle theta between the normal to the surface and the direction of the radiant flux d phi. This concept is known as the law of the cosine of irradiance. Moreover, irradiance E is inversely proportional to the square of the distance r from the point of source Q. This fact is also expressed as the law of the inverse of the square of the distance. So that means that these two things that are in bold, the law of the cosine of irradiance, that means that the radiant flux is directly proportional to the cosine of the irradiance, while if we are considering the distance between the surface that is reflecting energy and the sensor that is, in our case, for example, acquiring this energy, the quantity of this energy is inversely proportional to the square of the distance. So if you are very distant, that means that there are a very poor quantity of energy that will strike over your sensor. This law is valid for point sources, which are difficult to implement in practice. This is the reality. The assimilation to the scheme is valid with an error contained within the limits of the 1% when the source Q is placed at a distance r that is at least 5 times greater than the physical dimension of the source and is observable from any point belonging to the surface dA1. So that means that if the distance r it is at least 5 greater than the physical dimension of the source as observable from any point. That means that having our sensor far hundreds of kilometers from the Earth's surface, that means that this assimilation could be valid for our data, because they are all acquired in that sense. Let me check simply if I'm still continuing to register, to record. Yes, this is. And let's continue with the presentation. So, if we are talking about the hemispherical space, finally, consider the propagation of electromagnetic energy in space, considering an hemispheric model, as such is in the case of Lambertian surfaces. In this case, the m of the irradiance, so the excitance of the irradiance, recalling the definition of radiance L, can be expressed as follows. So, you see, we are calculating this quantity here, in which, in geometric terms, the solid angle d omega that subtends the elementary area dA affected by the radiant flux coming from a point Q or incident on it, in the case of an incident flux, can be expressed using a function of the angle theta and phi as the diagram of the following figure. So you see, this is our schema. Well, you see, it's nothing more than what we saw before. While here we are not considering only a particular direction, but here we are considering the hemispherical space here. And why so only this hemispherical space? Because again, this surface S is an opaque surface, so it's not transmitting any energy. So if the surface S is represented by a rho coefficient, a reflectance coefficient that is more than 1, that means that it will reflect energy, and it will reflect energy only in the upper hemisphere. So I mean, these are the different quantities, the normal, the incident angle, and the reflection angle theta 1, and here you have to imagine also that the fact that we are in a radiant flux that has, for example, this aperture, the phi and the theta, that is the aperture of this point Q that is reflecting energy in this particular position. So, stating that we are in this condition, now we can also have the only proof of a theorem that I'm going to ask you during the final examination, because now we are just try to demonstrate, to have proof of the Kirchhoff's theorem. So, remembering that, given a real homogeneous and isothermal surface, its spectral and directional emissivity coefficient, epsilon, that is, of course, it's a function of lambda, of wavelengths, and of course a function of the incident angle and the reflection angle, is defined as the ratio between the real radiance emitted and that which would be emitted by a black body surface, placed as the same kinematic temperature according to the following relation. You remember, when we have introduced the emission coefficients, that is again ranging in the wavelengths, we mentioned the fact that we can represent the emission coefficient as the ratio between the radiance of the real surface that we are considering, divided by what the radiance of what can reflect or emit a black body in the same range of wavelengths. And we mentioned the fact that this is a coefficient, the epsilon, so it's a dimensional quantity that is ranging between 0 and 1. and the epsilon will be 1 when we are facing, of course, a black body, is less than 1 for every single real surface. Alright? So, how we can have the demonstration of this Kirchhoff theorem? Well, let's see these figures. So, here we have, you see, that is very non-regular surface, because this is a radiant cavity. You remember we mentioned the radiant cavity, and we know what a radiant cavity is when we introduce all the topics related to the radiant laws. So you see here we have a very large cavity, and you see here, look at the mouse, we have a very, very small aperture to the external environment. This is a radiant cavity, and in this radiant cavity we have two very small surfaces, dA and dA1. So dA is a very small surface of black body, while dA1 is a very small surface, it's an infinite surface of gray bodies. All right. So, which are the characteristics of these different surfaces? The different surfaces, the radiant core cavity is simulating a black body, but of course is not a black body. So that means that if we need to characterize that with the Kirchhoff's law, that means that, this radiant cavity will be characterized, being of course opaque, is characterized by tau equals to 0, that rho is more than 0 because its reflecting energy is simulating a black body, but it's not a black body, and of course the alpha coefficient is less than 1. These two infinite surfaces, the dA, we said that is a very small piece of a black body, so that means that alpha is equal to 1, and then, of course, rho is equal to 0. Again, dA is opaque, so tau is equal to 0. dA1 is a gray body infinite surface, opaque again, so tau is equal to 0, but rho is more than 0 because it's not a black body, and of course alpha is less than 1. These two surfaces, infinite surfaces, are positioned at the distance r, and r is the line that is joining the two barycenters of these surfaces, and the normal to the barycenters and the line R are forming two different angles: the angle theta for the surface dA and the angle theta 1 for the surface dA1. All right? So these are the conditions. And you see the normal here of the surface dA and the normal here to the surface dA1. So, how we can now calculate the flux? Because if we are in an isothermal condition, so that means that we are measuring the energy the two surfaces are exchanging each other inside the radiant cavity, and isothermal conditions means that we are measuring these fluxes in a constant temperature. So we are, for example, in a lab, we have this radiant cavity, we have two different surfaces, and we have spectrometers, and we are measuring inside the radiant cavity the energy that is emitted by dA and what is emitted by dA1. If we have an isothermal condition, that means again that the temperature is constant, what is emitted
by dA to dA1 and what is emitted by dA1 to dA should be, equal. We need to equalize the radiative flux exchanged between these two surfaces because we are in an isothermal condition. So if we are calculating, for example, the radiant flux that is emitted by dA, that is the black body, to the gray body dA1, we have what? We have this quantity. This quantity, that is of course dP Cn, this is in Italian corpo nero, that is the black body. Of course, being an infinite surface, the radiance that is emitted, of course, it's also very small. That means that this quantity will be equal to the excitance of a black body that is multiplied from this ratio that we are calculated by taking into account what we said before of the irradiance and between the distance of the two surfaces. So that will be the excitance of a black body multiplied for dA cosine theta times dA1 cosine theta 1, that is the apparent emission surface and the apparent receiving surface, divided by this quantity, that is the inverse that we mentioned before of the distance, of the squared of the distance. All right, so this is the quantity of energy that is emitted from dA to the dA1. I forgot to mention that these two surfaces are emitting energy simply because they have a temperature that is above the absolute zero, of course. So, continuing, if we are calculating the energy that from dA1 is going to dA, so from the gray body to the black body, this quantity will be dPCG. Cg means corpo grigio, that in English is a gray body, that will be equal to the excitance of a gray body multiplied the apparent surface of emission dA1 multiplied cosine theta 1 times the apparent surface that is receiving energy of the black body, that is dA cosine theta divided by the square of the distance r. All right. So now, if we can equalize these two fluxes, because we are in isothermal condition, so we need to equalize these fluxes. But it makes no sense how we can equalize an excitance that is coming from a black body and an excitance that is coming from a gray body. It's not possible, of course. It makes no sense. So that means that something is missing. And what is missing? However, the gray body surface, dA1, is emitting energy, but of course, considering that is a gray body, is rho coefficient, the reflection coefficient, we mentioned the fact that being a gray body is more than zero. So that means that what is emitted by the black body and is insiding over the gray body, part will be absorbed, but part will be reflected back to the black body. So the black body is emitting energy, and part of this energy that was emitted towards the dA1, that is the gray body, will be returned back to the black body due to the fact that the gray body has a reflection coefficient that is not equal to zero, because it's a gray body by definition. While all the energy that is emitted by the gray body that is striking over the black body, again by definition, is completely absorbed, because it's a black body, so rho is equal to zero. and alpha is equal to 1. So all the energy that is emitted by the gray body is completely absorbed by the black body. And this is not vice versa, because as I mentioned, part of the energy that is emitted by the black body that is going to the gray body, part of that is reflected back to the gray body. So how much is this energy? This energy, simply considering that we can use this representation here. So, considering that all these surfaces, the radiant cavity and dA and dA1 are opaque, that means that the principle of energy conservation is equal to alpha plus rho equal to 1. And then, of course, if we want to characterize rho, so the reflection coefficient will be equal to 1 minus alpha, of course, because we are not considering tau, because they are opaque bodies. So dA reflected energy, dA1, I'm sorry, so the energy, the fraction of energy that is reflected by the gray bodies back to the black body will be this one. So this quantity of energy that is coming from a gray body will be the energy that was emitted by the black body, so the excitance mCn, that is multiplied by 1 minus alpha, that you see here, is equal to rho. So I mean, all the energy mCm of the black body, the excitance of the black body that is striking over the gray body, will be reflected with a quantity that is proportional to the rho coefficient that comprises between 0 and 1. Then the rho coefficient is equal to 1 minus alpha, multiplied the apparent surface that is emitting energy, dA cosine theta, times the apparent surface that is reflecting energy, dA1 cosine theta 1, divided by the square root of the distance, as before. So we have this quantity more, that is the reflected energy. So, if now we are equalizing the fluxes, what we'll have? We have that the energy that is emitted by the black body will be equal to the energy that is emitted by the gray body plus the quantity of energy that is this one that is reflected by the gray body towards and back to the black body. All right? So what we can do? The first things we can do is just to observe that this quantity here, that are, these two quantities here, this one and this one, if you see here, can be, of course, simplified. And what they represent, this quantity, dA cosine theta, dA1 cosine theta 1, divided by the square distance between the two center of gravity. They represent the mutual position of the two surfaces, of the two infinite quantities, inside the radiant cavity. So if we are simplifying these two quantities, I'm sorry, that means that this equalization of the fluxes is independent in comparison with the position of these two surfaces inside the radiant cavity. So whenever I put these two surfaces in comparison with each other inside the radiant cavity, the equalization of the flux will be the same. So this proof, this demonstration of the Kirchhoff's theorem is independent from the position, from the mutual position of these two infinite surfaces inside the radiant cavity. So, simplifying, we will have this quantity here. And if we are going to calculate these things here, we will have that the excitance of the black body will be equal to the excitance of the gray body plus the excitance of the black bodies minus alpha, that is the absorption coefficient, times the excitance of the black body. So, if we are again simplifying these two quantities, so the excitance of the black body that we have in the left and in the right term, we will have at the end that the absorption coefficient alpha will be therefore equal to these two quantities, to the ratio between the excitance of a gray body divided the excitance of a black body. But you remember, the relation of epsilon, the emissivity coefficient, stating that we have the same quantity here. So the emission coefficient, by definition, is the ratio between the energy that is emitted by a gray body and the energy that is emitted by a black body, being these two bodies in an isothermal condition. That is the same condition for which we process all these equalization of the fluxes, extracting alpha. So that means very simply that we can assume, and this is the proof of the Kirchhoff theorem, that alpha is equal to epsilon. So I mean, in isothermal condition, that means that the absorption coefficient is equal to the emission coefficient. I'm sorry. This equality allows us to better understand the Planck's law, which originally formulated only for black bodies can also be extended for gray bodies, considering that epsilon is less than 1. The principle of energy conservation, generalized for opaque bodies, turned out to be what? Now we can substitute epsilon to alpha, so we can say that rho plus epsilon is equal to 1. So what does it mean? And this is very important after this proof of the Kirchhoff theorem, just to state that a very emissive surface will therefore be little reflective and vice versa. So if rho is very high, of course, epsilon turns to be very low and vice versa. So if a surface emits energy, that means that it will be reflect a poor quantity of energy and vice versa. It should be noted, however, and this is very important, that this is of course completely true from the theoretical point of view, but that this principle applies only to isothermal conditions, as we mentioned before, and therefore not in the real case of acquisition with multispectral sensor. So consider our images that we initially used, for example, during the labs. So there are images that require over a surface, a very large surface, that is not in isothermal condition, because I mean the temperature of the different surface. Think about the area of the Piedmont we are using in the lab. There's, you remember, band 6.1, that is the relative, that is in some way may be compared to the relative temperature of the different surface. Of course, the the clouds are colder than the water of the sea, and the water of the sea is colder than the for example the built-up area. So I mean, this is not an isothermal condition. The different surfaces are not in the with the same temperature. So I mean, that theoretical condition, unfortunately, we could apply that to real measurements. But this is important to say, but this is of course important to understand that this proof of the Kirchhoff theorem gives us the possibility to substitute alpha with epsilon and vice versa. So when we are talking about the reflection, the phenomenon of reflection is governed by the physical characteristic of the surface involved, so that there is a double behavior as previously anticipated. You remember, now we are trying to analyze the surface from the very geometrical point of view. So we mentioned before that we can have this particular condition. You remember, before we saw a couple of figures where we have a very geometrical representation of that. Now we have the same figures in which we have something that is most realistic. So you see, this is in the left side what can happen with specular reflection, and you see this is something similar to a mirror, to a marble surface, to a very polished surface, in which also the incident flux is divided into the three visible subbands, red, green, and blue. And you see, with a specular behavior, the energy in the visible is reflected with the same angle of incident if considering the normal to the point of reflection. And you see also from the spectral point of view, in this very pictorial representation, there are no changes. I mean, you can see the energy that is reflected in the same way. Also from the spectral point of view, the same quantity of red, green, and blue are reflected by a specular surface. Well, when we have diffuse reflectors, that you see is a surface that is rough, is not very smooth like this one. You see that the energy that is coming, for example, from the sun in the visible is reflected in an hemispheric, from the hemispheric point of view, in a very different, in very different direction. That means that, as we mentioned before, this is a Lambertian surface. The reflection is independent with respect to the incident angle. But from the spectral point of view, you see here we have red, green, and blue arrows. From the spectral point of view, the reflection could be changed in comparison with the specular reflection. That means that from the spectral point of view, we can have a mix of the reflection, in which in particular direction is dominant, for example, the red part of the visible, while in other is dominant, for example, the green one. So this is an anisotropic model, the specular reflection in one single direction. Here we have anisotropic models in which the reflection is happening in all the upper hemisphere of the surface, considering again that these two surfaces are of course opaque, so they are not transmitting any energy. So the separation between smooth and rough surfaces depends on the scale of analysis. So indeed a good criterion of distinction can be that of Rayleigh, according to which the limit of smooth surface is defined by the relation. So I mean now we are taking into consideration this relation that is very simple, that is called Rhylith Relation. Again, Rhylith as in the scattering, in the selective scattering, in which with this relation we can understand if the surface is smooth and so it will behave as a specular surface, or it's rough, and if it's rough it will behave like a Lambertian reflector. And this relation is very simple. So the smooth surface is a surface that has this particularity in which h is less than the ratio between lambda and 8 times cosine theta. What are the meanings of these different things here? The meanings is that h is the height of the discontinuity of the surface. So, for example, if we are taking into consideration a remotely sensed image, for example, what we used in the first labs, for example, think about the northwestern part of Italy, so which are the height of the discontinuity of the surface, considering that, for example, if we are in a built-up area, of course we will have a point on the road level and, for example, to the roof level. So that means that h could be many meters, dozens of different meters. If we are in the vegetation, it's the same. If we are taking into consideration trees, points on the ground and on the top of the crowns of the trees will be again meters and meters. And also for other kind of vegetation, for example, we are not meters, but we have, of course, many tens of centimeters, for example. And also for what we are considering, for example, smooth, the sea, for example, the sea is not smooth enough at all, because we have to consider the wave motion. So if we are considering the wave motion, the difference in height between the top of the wave and the other surface will be some centimeters, some tens of the centimeters, or some meters if the wave are very high. So that means that this h quantity is at least some centimeters in the worst case for images acquired from satellites. What are lambda? Lambda, of course, is the wavelength of the incident electromagnetic energy, and theta is the incident angle. So how we can consider that more generally, so let's get back, if this relation is valid, that means that the surface will be smooth. So that means that will act as a specular surface. So if this quantity here is bigger than this one, all the surfaces, this kind of surface should be considered smooth and then specular. So let's consider how much these things value for in reality for our application. So if we are considering images that are acquired in the optical window, that means that this lambda value is very small. Should be fraction of microns for the visible, or very few microns if you are considering the near and middle infrared. While this quantity here in the denominator, 8 cosine times cosine theta. Cosine theta is the incident angle of the sun, considering that the acquisition is more or less never done in perpendicular conditions, so the sun is never perpendicular to the surface. But of course, this value is rather big. Could be something like 8 multiplies something that is less than 1, but not much less than 1. So that means that this quantity here are microns divided by some unities. So I mean it's a very small quantity. And we mentioned that here, that h in real cases could be some centimeters. So of course this condition is never true for real surfaces and from acquisition with passive sensors. That means that if it's not true, this means that all the surfaces are not smooth at all. So, I mean, they are not specular, but all the surfaces that we are analyzing over the Earth's surface, being this relation not true at all, that means they are not smooth, but they are rough. If they are rough, that means that we are sure that in the real cases, when we are acquiring data from the satellite, all the surfaces we are acquiring data, reflection data, consider the classical image we have been used in the first labs, both the water of the sea, in both, for example, the built-up area of Torino or the harbor of Genoa, and both the cultivated fields or the forest, are all rough surfaces. So if they are rough surfaces, that means that are behaving like isotropic reflectors. That means, and I'm going back of some slides, we are here. So we are in this red case here. Look at the mouse. So if the satellite is perpendicular to the surface, that means that independently from the incident angle of the energy that is coming from the sun, if this energy, if this surface that is rough is reflecting energy, that means that the rho coefficient is more than 0, that means that part of this energy will go straight to the sensor, and if enough in terms of power will be registered on board of the satellites. If we are in this condition, of course, the energy, the surface could be reflect energy, but in a divergent position, and so on my sensor I cannot, in this case, record any energy. So, considering this Rhylith criterion, it is possible to face surfaces that are smooth, and so they are behaving as specular surfaces. Yes, of course, and this depends on the lambda. On the lambda value, and of course that ratio could be greater than the difference of haze, of the discontinuity on the ground, only when lambda is very big. And when it's big, in our case, in our remote sensing, we mentioned the fact that the bigger, in terms of wavelengths, spectral bands we are using is the microwave, that you remember is ranging between at least ½ centimeter to 1 meter. So, for example, if we have this lambda that is 1 meter, that could be satisfied, this equation here. So that means that the surfaces are smooth, and so they are acting like specular surfaces. And this happens, of course, in the microwave, and in the microwave we can, and this is why it's quite difficult to interpret this image, we can have interpretations that are based on the power of the energy that is reflected, but also on the fact that we can extract from radar images smooth or rough surfaces. And these smooth or rough surfaces are representative of some particular phenomena. And this particular phenomena, I will introduce this particular phenomena just at the end of the course, when we will talk, if possible, to radar images, especially in the lab. All right. So, in the case of acquisition made by multispectral sensor placed on board of satellite platforms, which orbit at altitudes higher than 400 kilometers, if we consider the wavelengths of the visible and infrared, as I mentioned before, h is always greater of lambda, so all the surfaces, and this is in bold because it is very important, are to be considered rough, and therefore Lambertian. This ensures that the sensor always receives a fraction of reflected radiant flux, and that therefore the failure to record this flux is characteristics of surface framed with alpha that is equal to 1, black bodies for such wavelengths in the hypothesis of opaque surface. So that means that these things here is simply to admit that if we are registering image data with passive sensor, if we get a null radiance coming by reflection by the Earth's surface, that means that, of course, on the hypothesis that these surfaces are opaque, that is always true, that means that the surface that is imaged is represented by an alpha equal to 1 coefficient of absorption, of course. And this is very important to say. So, this last statement, given the variability of rho with respect to wavelengths, does not apply to all incident lambdas. especially for long wavelengths, as I mentioned before, microwaves, surfaces that are opaque in the visible and infrared, they can become smooth and therefore behave like specular reflectors. So again, as many of the different phenomena we saw till now, also the, let's say, the roughness of a surface is depending on the wavelengths of the incident energy. So again, a phenomena that is function of wavelengths. So the same surface that, for example, in the visible is rough and so is acting, is behaving like a Lambertian surface, could become smooth for very long wavelengths of the incident energy. For example, the sea could be Lambertian and is Lambertian in the visible and in the near and middle infrared, and for example, in very long wavelengths of the microwave, could be smooth and then acting like a specular surface. So I mean, you see, another things that is function of wavelengths. In such cases, therefore, the absence in which, the surface is specular, is smooth and then specular, in such cases, as I mentioned before, therefore, the absence of a reflected flux recorded by the sensor could mean two different things: that a surface have an alpha equal to 1, so is not reflecting, and a surface that has a rho that is more than 0, so is reflecting, which however reflects in a direction diverging from the sensor, like I mentioned before. So I mean, you see that for radar sensor, you should take into consideration these things here, that of course is making the interpretation of the image harder than for a passive sensor when we are using active, because you have always, for the same cell of the image, this possibility, these two different possibilities. And so you need to understand if, by experience especially, if the surfaces are smooth or rough, so if they are specular or Lambertian. Okay. I think that that's it for this fourth part of this lecture. So I mean, the interaction between electromagnetic energy and the surface is ended in this first part. I'm just checking that everything is okay. So this first part lasts for 1 hour and 15 minutes more or less. So we will meet again for the second part of this lecture 5. Of course, take care, and we all never give up.